And for this specific easy set of things to do, I'm going to ask you to go back to the RCSB website. And what I'm going to teach you is how to use the interface to gain access to the information. Now, this particular version of the PDB database, it's very straightforward in the sense that it's designed to be used as a learning tool. So, for example, there is this list of things on this side that are, well, kind of easy to understand. If you want to deposit data, clearly you go to this item. If you are looking for searching, visualizing, analyzing, or downloading, you pick any of those. And then there is Learn. This website, because it has this focus in learning, it changes quite often. So if you click on Learn, for example, what you get is these resources that without guide might be difficult to follow, but one of the easiest and not often emphasized enough, in my opinion, is this one over here, the molecule of the month. If you click on that one, it's going to take us to a list of all of these molecules of the month. Of course, you need to go to Learn on the left, and then molecule of the month. I'll go back so you can actually see it. So this is the main website, rcsb.org. Learn, molecule of the month is almost at the top. And that gives you this index of molecules that have been considered molecules of the month. Ideally, I guess the original idea was for this to be follow through time. That is, if you used to log with certain frequency to the website, you will run into a specific date for a specific molecule. But other than that, they are sorted alphabetically. So it's fairly easy to find something if you know the name. For example, the molecule we've been dealing for almost 2 months, hemoglobin, you can click on the H, and almost immediately at the top of the page, you have hemoglobin. Now, these sets of molecules of the month, if you click on hemoglobin, what you're going to find is the modern equivalent to the old-fashioned paper store monograph. It's a fairly brief description of the protein, some historical data, and sometimes some animations, as you can see here. Here on this slide or in this image, left of the cooperation makes it easier. What we see is an animation that it's taken several structures, just such as the ones we saw before, where there is no oxygen, there is an oxygen molecule, and it's bound to the iron. And what it's modeled or displayed here is how the enzyme, or the protein in this case, is changing its conformation depending on the binding. Hemoglobin has a very complex behavior in that it's an allosteric protein. So it changes conformation not only on one subunit, but on the 4 of them. Here, I think, for the case of hemoglobin, if you read through this section, it's talking about the sickle cell anemia and how that mutation that we have already read about in OMIM, in UniProt, and even seen the structure, causes that on the right, that not only hemoglobin works, but it forms these strands inside the red blood cell that change the shape on the red blood cell. So as I emphasized last class, in a way, structural biology, the PDB, or every structure for a protein, try to follow this pattern of structure and function and the relationship between those two. Of course, there's many ways to reach this page. The easiest is through this molecule of the month. Sometimes this index is not following a name, but a function, as is the case of G. If you go to that section, you can find this case glycolytic enzymes. It's not only one protein, but the whole, let's see, how many should they be? 1, 2, 3, 4, 5, 8 enzymes to take glucose and break it down all the way to pyruvic acid. And in the case of that section, if you click here, it's not going to be a short monograph, but it's gonna be, oh, actually 10 enzymes, sorry. It goes all the way to the pyruvate kinase, with a few lines describing what is interesting, what is important about them, in such a way that if you have no idea how they look like, you can get a quick glimpse at very, very diverse sets of characteristics. Let's see, let me go back. Yeah, so I wanted to use this one on the top. This is the same entry for glycolysis to point out a few things. If you take a quick look and focus only on the colors, it turns out that there's only one protein in the whole of the glycolytic cycle, that it's a monomer. The rest, dimer, maybe this is a monomer, I'm not entirely sure, dimer, at least trimer, maybe tetramer, tetramer, trimer, dimer, tetramer. This is, in the terms of the glycolysis and in terms of metabolism, more the norm than the exception. Many, many proteins are going to be hetero-oligomers. Sometimes of the same, well, sometimes homo-oligomers, as is the case of triose phosphate isomerase. In the case of the pyruvate kinase, that's a homotetramer, but you can have all types of combinations. Okay, so that is for a brief introduction. I'm going to go back to the main page, RCSB. And in general, this search is very useful, but only if you have an idea of the code of the protein you are looking for. As opposed to UniProt, the search engine in this database, it's kind of lame. So if we knew already, for example, 5WOG, which is a protein we use, we plug in the code, we're going to find it. Without trouble, straightforward. But don't do that. I'm going to show you the other way to find things. Here, it's advanced search. And this advanced search is actually easy to use and much more powerful. Although it could be weird at a first glance. So for example, instead of having just a place to type something, here we have to select what type of information we are looking for. And if you just look at the first ones, it's actually quite difficult to look for something unless you have a UniProt number. If you already have a UniProt number, you can select UniProt accession number and plug it in. Do you remember any? It doesn't matter. The point of these searches is that they should be easy. Even if we don't have that information, we should be able to search for something. So let's ignore this one for a moment. What other things can be found here? Well, you can use general text, gene names, structure titles, macromolecule name. Remember, from biochemistry, this will be the name of the protein, the name of the nucleic acid or the lipid, or even saccharide. Pathway reaction name, author, if you are looking for a paper, a publication. Let's see. Look at this version down here, or this option over here. You can look for a wild-type protein. In the PDB, as opposed to UniProt, many proteins have been mutated because the process of obtaining the structure sometimes requires those mutations. So it's very often, more often than not, that you only find a mutant and not a wild type. Chain length, if you already know hemoglobin 147 residues, you could try to do that here. And I'm going to select this one just to show you another interesting feature of this search. So chain length, and it gives us a range. Let's say between 140 and 150. And before actually searching, over here we have, over to the far right, we have a button that counts how many results can we get with this query. And if you click result count, it's going to perform a search. And as a query, as a way to search in the database, it's pretty bad because I almost get 10,000 results. That means that within this database, there's between 9,100 proteins that have that size. Is that useful? Well, maybe it is, maybe it's not. Let's refine the query. So, as opposed to UniProt, where we could type an AND or an OR in the query, Here we have to do it adding another search criteria. So if you look to the far right, you need to click on this plus button, and you're going to get another entry for the search. And this entry can have any of the other items that we have already seen before. For example, let's see, let me go back all the way over here. Sequence motif. Do you know what a sequence motif is? Well, there's patterns, for example, for protein phosphorylation, protein glycosylation. Remember, cellular biology, glycosylation only happens in asparagines and glutamines. If we know of certain patterns that predict glycosylation, we could look for them here. We could look for protein modifications. Remember the phosphorylations we talked about? We could ask for those, or even glycosylation. So why don't we click on that one? Protein modifications. And look over here. We could use all of these variations to look for modifications, a name, a keyword, a res ID, and others. Probably the name is the easiest because even if we don't know a lot of chemistry, it's easy to identify that these are amino acid related chemical modifications. Let's see. Let's try to find a phosphotyrosine, for example. A phosphorylated tyrosine. Well, I find the phosphoric aspartic acid. That should be a phosphorylated aspartic. It's not that hard to find, is it? Well, try to find exactly that one, so we have the same in common. I need right. Don't you find this kind of odd, that you can look for stereoisomers of asparagine? Where do you expect to find those? But where? In the bacteria? Or where in general? Actually, bacteria is not the only source. Otherwise, we wouldn't have antibiotics. Where does protein synthesis happen in any cell? In the ribosome, right? And where are the exceptions to that? There's exceptions. There's protein synthesis that do not happen in ribosome. No. Still uses ribosomes. Fungi can synthesize proteins not in ribosomes, and that's how many antibiotics are generated. But, well, that's beside the point of the class, but bacteria is not the only source. Already selected that? Click on this L-aspartic 4-phosphoric acid, and click again on the result count. Okay, I was expecting 24 structures, so that is not too bad. We have a couple of examples of things with that modification that are also small proteins, right? 140 to 150 amino acids. So what we're doing here is exactly what we did in UniProt, using species and name, for example, or something else. We are reducing the possibilities in the search. Everybody up to this? Okay. So now that I have those results, I could actually click here on the 24 or down here on submit query. The result is going to be pretty much similar. Here we have a list that includes the length of the sequence as well as the chemical modification. And the list, where do we get the number? Oh, well, we don't get strictly a number. But every single one of these results should contain those two pieces of information, and a specific length and the phosphorylation. And in fact, look at the title of this structure. Crystal structure of the phosphorylated receiver domain of the transcription regulator from Aquifex aeolicus. If we are looking for general information, we can use this query to generate a set, 24 proteins, that contain the specific amino acid we're looking for and that have a relatively small size. In these results, well, anybody has a question up to this point? No? There's other ways to even download all of these structures without even having to look at this page. But that is kind of advanced and maybe unnecessary. Sometimes we get this. In this list, apparently, there's at least 2 different proteins from 2 different organisms that fit this criteria. Equifex aeolicus, and down there Tolipotrix, species C, whatever they are. If our query had been wider, let's say between 100 and 500 residues, we could have gotten different species. Sometimes, in the case of humans, you get thousands of structures because everybody wants to cure diseases. And sometimes you find proteins, a single protein from the weirdest organism because somebody was trying to crystallize just anything they got their hands on. So as opposed to UniProt and even NCBI or Assemble, this database is really, really biased toward things that people want to work with. Not only sequence, but to purify and crystallize. So in a way, even though the database may contain thousands of structures, it's rather restricted in terms of what material is available. Now over here, there's a little thing that is actually interesting. Here in these tabs, we have citation entities and ligands. And ligands sometimes is pretty interesting because this amino acid doesn't have to always be part of the sequence of the structure you're looking at. Sometimes, whatever you're looking for is a ligand. For example, if you wanted to understand how a toxin interacts with hemoglobin or with any other protein, an antibiotic with a ribosome, you look for the ligand, you look for the molecule that is the drug or the medicine or whatever it is, and you may be able to look at the structures that contain that drug. So to test that, let's see if it's pretty useful. What would you type for a search? What drug? It's easy to find and simple chemically. You think we could find paracetamol here? And look, the search was actually pretty quick. I found a bovine lactoperoxidase in complex with paracetamol. So if I wanted to try to study to understand the interactions of that drug with a protein, that is the way to go. Now, by what you know and the tools you can use, even if there's no structure of a human protein crystallized with paracetamol, you could use this one, the tools for sequence analysis, the sequence from an equivalent in human, and locate it through BLAST or any other means, and compare them and actually make a prediction that for humans, for that same protein, the same drug could interact in the same spot. Or not. Maybe the sites are totally different. They contain the opposite charges in the amino acid. So for the last structurally related website I'm going to show you, I'm going to take this result, the 3PY4, and plug it into this other database. This one is called PDB-SUM, PDB-SUM. The idea of this other database, of the PDB-SUM, is at a glance. It's going to try to give us information that you don't have to read page after page after page to understand. It's going to be summarized. Oh, so sorry, I click on the wrong one. Where is the right link? Aha. Okay. Everybody managed to get here? Yes or no? Say no if you haven't. So I'm going to click over here so you can see the address. What did I do? Oh, it's pretty ugly, huh? So no, it wasn't the first. I'm going to go back to the first result. This is the first result. You need to click over here to the top where it says PDV Zoom, and it's going to take you to this page.
Okay.
And this is the right one. I don't know why the first result was the other one, but this is the useful one. And we are looking to place 3PY4 in here. Before you click OK, or even if you already click OK, notice that this one is still pretty useful to look for things that you don't have the code for. Here we already have a code, but you could have used a text search for paracetamol again, or a sequence, or UniProt code and assemble ID in case of you having DNA instead of protein, or even a family ID that we haven't studied, but they compare a lot with UniProt or assemble. So click find 3PY4. Now this looks totally different, totally unlike all of the other databases. The color scheme, it's like Christmas candy colors. I don't like it. But what it does very nicely and very quickly is this. Here we have the sequence and the secondary structure. And over here on these tabs, we have specific information for the proteins, for the ligands, for the metals, if there's grooves on the surface, if there's pores, tunnels, and other information. Because we came looking for the interaction between paracetamol and this protein, what we want to look at is ligands. So if you click on that, remember the idea of this site is to have things at a glance, and that's why it has this long list of molecules that are not the protein. And if you click on any, we actually can click on this one, TYL. And what should happen is that the page is replaced with information pertaining TYL or paracetamol or Tylenol or whatever name you know it by, the chemical structure. And if you scroll down, hey, what happened here? If you, well, here did you see something? Oh, there we go. Here is that Tylenol, paracetamol molecule, and here the residues that this molecule interact with are indicated. There's a histidine that makes a hydrogen bond, and all of these amino acids are making like a hydrophobic surface for the paracetamol to bind. So if we wanted to compare the sequence of this bovine protein to one from human, those will be the amino acids we are interested in the most. That is one way to display it. If you click on the PDF file, you can get another one that is actually very easy to print, and it should have, oh, it doesn't have it. It should have a legend to indicate that these type of symbols indicate hydrophobic contact, and only those with lines and with numbers indicate hydrogen bonds. It's kind of funny that that molecule doesn't use any hydrogen bonds on this side, only on this one. Even though there's a negatively charged amino acid, a positively charged one. And the heme group makes some contacts. So that's it. The purpose of PDV Zoom is that, to summarize information. If we wanted to look at other molecules bound to this protein, they are pretty much summarized here. The heme group, polyethylene glycol, and some other molecules that are used for crystallization. Over here, this protein turns out that it's glycosylated. Any questions? No? Would you like to take a look at that glycosylation? I know those of you that took cellular biology, I don't think we ever look at one glycosylation in a 3D structure, did we? No? Would you like to take a look? Well, let's do it. We have a good code over here. The the 3PY4. So open your Chimera. And go to File, Fetch ID, and type 3PY4. Oh, sorry, 4. Fetch by ID. I'm going to use my usual settings, the preset interactive one, then the publication one, and we should be able to see at a glance that over here there's the heme group, and here we have the glycosylations on the surface. One here, one over here, one down here. The presets, go for the publication and the interactive ones.
Can I ask a dumb question?
You can ask any kind of question.
Why do they have like arrows? What do the arrows mean?
The arrows, again, the nomenclature here is the helices are alpha helices. And the arrows are either beta strands or beta sheets. That's the case of a beta strand because it's only one. But back here we have a beta sheet. As far as I can tell, this is a very alpha helical protein.
So it's like the combination?
Here, let me show you a diagram over here.
Yes.
So this is that very same protein represented by structure, a beta sheet, a beta strand, alpha helices, beta, and everything that has no symbol, it's supposed to be a coil, a random sequence. And this diagram even includes disulfide bonds between regions of the protein. Yes? This is PDB zoom. I clicked on protein. You can get it in many ways, but this one, the one that's already made and easy to read, PDB zoom. This one is a display that shows everything as if it was flattened based on the sequence. And in Chimera, what we get is the 3D structure. This very same diagram you can get as a PDF file and use it if necessary. What it doesn't show, again, because this is protein structure, is what we can look in here, the glycosylations. Yeah, there's something about glycosylations that they seemingly occur in 3D space near a tryptophan. This happens also in the influenza virus. So who can tell me how I could find where the paracetamol is located? Well, the easiest way to do that is just go to residue and locate the TYL, click on it, and after doing that, just focus. And there it is. Yeah, so the easiest way to find this molecule, because we know the code by now, is go to select, residue, find the TYL, click on it, and after that, go to actions, focus, and it's going to take you straight to where that molecule is. And whatever this enzyme do, it's right there in the binding site with the heme group. If this was a protein binding oxygen, probably the interaction with the paracetamol will block that other interaction, right? Simple physics, two objects cannot occupy the same space at the same time. Here in PDB zoom, I'm going back to PDB zoom, in the top page, you can find the equivalent to the function or the catalysis that we find in UniProt. So this protein is an enzyme that it's a peroxidase. Do you know what's the function of a peroxidase? To break down oxygen, dioxygen peroxide. So it's an enzyme that breaks down hydrogen peroxide. It makes sense that paracetamol can block that because of the oxygen in the phenolic group. And again, it will likely block that function.
What is TYL?
Why the code? Or why? What is it?
Both.
Both. Well, let's see. To answer that question, I'm going to go back to the PDB Zoom and click on the first one. And as I showed you before, the information here includes down here the sequence, and over here the list of all of the chemicals in the crystallization. And here we go. This is TIL, N4 hydroxyphenyl acetamide, Tylenol. But why the TYL code was assigned? It's coincidence. These codes are assigned upon the position of the data, and it could have been 1EN. Doesn't have to make sense. Or at least that's the way it's supposed to be. I don't want to go into the details of that part because computationally, the files that have the structures are made only to have 3-letter codes because they started being for amino acids. So ASP for aspartic and all of the combinations, and the ligands inherited that scheme. So the name's not always going to make sense. For example, this one, N-acetylglucosamine, well, maybe they try to make it similar to the name, but it's not always going to work like that. So in a way, it's arbitrary. That's what I'm saying. Sometimes, because of drug design, the molecules don't have a common name. They only have UPAC names, and the codes are totally irrelevant. Calcium is pretty obvious, Ca, mannose. Glycerol, I have never memorized it. Iodine, for whatever reason, they use 3 letters, whereas for calcium they use 2. Thiocyanate, SCN, I would have forgotten that ages ago. Oh, here, there is actually, I haven't thought about this, but when there is a phosphorylated residue, just as the case of cysteine, it's indicated in modified residues. The N-acetylglucosamine should also appear here somewhere, but this is generally identified as a different amino acid than just the serine. Okay, any other questions? However you want to call them. No? Really? Okay. Then my last trick. Do you still have open Chimera? Okay. So go back to Chimera, and this is part, or not part, but it's going to be tied into the exercise I promised to get used to how DNA is read. Close the session, not the program, just the session. Go to Tools, Structure Editing, and click on Build Structure. Go to Tools, Structure Editing, and Build Structure. Okay, everybody there?
Yeah.
Okay, cool. We should get that window. The first 2 are totally weird, right? Unless we are really, really good, building something atom by atom is going to be tough. Fragment is not that difficult because, as the fragment implies, you can select specific types of molecules. But I think it's a waste of time to do it here. My personal opinion. PubMed KMID, we haven't talked about that, but it's similar to the PDB code. If you have a code for a chemical, you can select it here and just build that structure. Peptide, it's cool, but we are not going to use it. Skip all the way to helical DNA. Now, let's write a sequence. And let's make it simple. A, C, G, T in alphabetical order. A, C, G, T. Type it 2 times, 3 times. ACGT, ACGT, ACGT. Now it's simple, and it also has the important characteristic that it's not going to be read the same on the reverse, right? This is going to be our strand. Let's call it our coding strand, and we wrote it from 5' to 3'. How does the opposite, the corresponding, the complementary should read? What will be the code in the complementary? It should be, no, it should be A, C, G. So it's exactly the same. Okay, that's not going to be useful. Let's change the 4 nucleotides in the middle to something that reads GGCC. So after the first T, CCGG.
After the first T?
After the first T. So the 4 nucleotides that are in the middle. Still palindromic, right?
Remove it or?
You tell me. Technically, I delete them and inserted them again. Yeah, you only should have 12 nucleotides in total. Ready? Now click on apply. And there you go. What do you think will happen? Well, I'm going to use my usual approach, interactive, in presets and then publication, so I have this high contrast. What do you think will happen if I select tools, sequence?
It's gonna give us a protein.
The protein? Why? It's going to give us the sequence in nucleotides. Did I create 2 of these? Yeah, apparently I click 1 too many times. Do you see only 2 chains or do you see 4? Only 2, so it's me clicking. Click on both and click show. And what we got is exactly the 2 sequences. However, notice what the program did. Even though this one is the complementary, is also shown from 5 to 3'. Even though it should be the opposite once it's annealed to the DNA. This is kind of the problem of always having to resort to 5' to 3'. That if you are not careful, you could be led to believe that those 2 are identical, which they are, but they are opposite strands anyway. Okay, well that's about it. Next class, we're gonna take a quick detour to one last database, and you're gonna love the name. We're gonna plug in a couple of names here. If you are currently under medication, bring the names. No? Well, you don't have to. But if you have anything that you are taking, why even flavored ingredients in food, bring them over and we'll look for them here. The reason I bring up this database is dual. One is for you to find information about them, about these resources. In the case of biologists, even anesthetics should be here. But there's another interesting aspect of this database, and it's that it's going to show us the official legal presentations of the drugs. If you're going to get it in a pill, in a capsule, whatnot, it's usually shown here. So it's pretty interesting to look at. Other than that, have a nice afternoon.